Hi, thank you for joining. So, is there a right way to run network functions on cloud infrastructure? My name is Dudi Cohen, I'm from DriveNets, and I'm going to discuss this topic in the next few minutes. Before we start, I want to mention that we hear a lot about network functions migrating to the cloud. Two very obvious examples are AT&T's move to move its 5G core functionality towards Microsoft Azure cloud infrastructure, and the cooperation between Dish, another 5G operator that is starting to deploy its network, and AWS, Amazon Web Service. So are those moves right? Will they succeed? Is there a difference between the control plane and the data plane functions when you do those moves? Before we answer those questions, I want to mention a few things about the motivation to go towards the cloud. So when you're an operator, when you're a mobile operator or fixed service operator or any service provider, you see your investment in the network growing significantly. The more capacity you need to serve, the more money you need to throw into the network. On the other end of the equation, you do not see the revenues growing. You see the ARPU staying basically as it is. You see your network using more and more resources while your revenues are not growing. And basically what you see is a very inefficient infrastructure or inefficient architecture in your network that serves your customers. So what do? What you do is you do what the cloud operators did a decade ago. You move from a monolithic infrastructure in which every network function, or in the past any application, ran on its specific server with specific hardware and software infrastructure, towards a more flexible, more agile infrastructure called the cloud. Now, this is something that the data centers did very successfully. This is something that network operators were trying to do for decades, going back to the NFV days. So we started from PNF, a physical network function, a router or network function which is monolithic, which has its own hardware and software and application layer coming from the same vendor. And we tried to break it into a VNF, a virtual network function, in which the software, the networking function software, ran upon a standard commercial off-the-shelf server with a standard operating system. This was very limited in terms of success and functionality because you were able to run only one network function on the server, and the scaling of this was very inefficient. In fact, growing capacity in this architecture turned out to be much more costly than running it on a monolithic PNF. So then came the CNF, the cloud native network functions, that basically took the cloud infrastructure, like AT&T did with Microsoft Azure, and ran the network function directly on the cloud. That gave you the flexibility to use a different amount of resources whenever you needed, the geo-scalability to run your network functions wherever you need, wherever there is a cloud infrastructure. But still something was missing. Still, when it came to data plane as opposed to control plane, the scalability just didn't work. If you want to run data plane functions, take 5G core, for instance, if you want to run the UPF, the user plane function, on top of a commercial off-the-shelf server, when you start to pump more and more capacity into it, you find out that you simply need too much servers. That's too much capex, that's too much space, that's too much power, etc., etc. And this is because the servers, the compute-based cloud, the x86 or ARM-based CPUs that are used in the cloud are simply not planned and not built to run network functions. Those I/O functionality or tasks simply take too much resources from your average day-to-day CPU, which is used in the cloud. And this is where NCNF, network cloud network functions, come into place. Because in NCNFs, you put on top of the CPU-based infrastructure also an NPU-based infrastructure. NPU is Networking Processing Unit. Those are ASICs that are built in order to fulfill high-capacity, high-rate data plane functions, I/O functions, networking functions. And this is exactly the difference between putting a control plane function on the cloud and the network plane function on the cloud. For network plane, you need an infrastructure which is built to run high-capacity networks. And this is exactly what DriveNets does. DriveNets build networks like clouds, but as opposed to the public clouds, to your AWS, Azure, GCP, whatever cloud you may run your control plane function on, the DriveNets network cloud infrastructure brings more than compute resources. It brings networking capabilities that allow you to run efficiently any network function on top of the cloud infrastructure and leverage all the benefits of the cloud. First of all, you leverage lower costs because with the networking optimized infrastructure, you get less hardware requirements for the same functionality and the same capacity that you need to run. More than that, you have optimal scaling. You can scale the network plane, the control plane, the fabric, or the packet forwarding plane separately from the other functions and in great efficiency. And of course, you get ease of innovation. You get faster time to introduce new service in your networks, new functions, new end customer services. You can deploy those over this network cloud infrastructure without having to add hardware, without having the need for truck rolls to remote sites. You just simply add a container and run the function in it. So how do we do it? How does the DriveNets network cloud different than any other disaggregation networking solution? So first we do disaggregation. We separate the hardware from software. We're a software company, so we do hardware and software disaggregation. But on top of that, we also do hardware clustering, hardware distribution. That means that we do not need a separate type or a different type of hardware for any network functions or any network size. We use very simple building blocks and we aggregate them into clusters. And those clusters are built upon multiple white boxes, but they are treated as a single hardware entity. That means that we virtualize all the cluster together with all its networking, compute, and memory resources towards the upper layer applications. Next, we do containerization. That means that it's not a single container, it's not a single network function that uses this cluster and all its resources. It means that we have multiple network functions of different types. It could be a core router alongside a firewall and DDoS mitigation application and a peering routing application. All of those will use the same resources, but will be separate and managed as a standalone entity. And next, after we did all this disaggregation and containerization and distribution and created something that is very hard to manage and to grasp, we do orchestration. The orchestration layer wraps it all up in a very easy to manage, automated infrastructure manner. That means that most of the tasks you do today manually, creation of new nodes, addition of line cards and ports, definition of VPNs, etc., those are all done automatically via the orchestration layer, which is the DriveNets orchestrator or the DNOR. So basically, we took the monolithic approach, the PNF, the standalone chassis, which has line cards, which has fabric cards, which had a chassis and a control plane, and we distributed it. We broke it into several functions. We have the NCP and the NCF, which are the network cloud packet forwarder, which is equivalent to the ports, to the line cards. We have the NCF, which is the network cloud fabric, which is equivalent to the fabric. We have the NCC, the network cloud control, which is equivalent to the control plane. And we have the DNOR, the orchestrator, which is in some sense equivalent to the chassis because it wraps it all or wraps it all up without the physical limitation of your traditional chassis, which limits your growth in terms of capacity and ports and power, etc., etc. And this is what brought us to the network cloud architecture. So basically, we have white box at the bottom of the architecture. Those could be acquired from any white box vendor. Basically, we do not sell the white boxes. You can go to your favorite vendor and buy it. On top of that, we have the hypervisor, the virtualization layer, which take those white boxes with their different type of resources, the compute, the memory, the TCAM resources, the networking, packet forwarding resources, etc., and virtualize them towards the upper layer applications. Those applications or service instances, as we call them, can run on top of it. Many service instances can run on top of this infrastructure as individual services. So from the operator perspective, you still see those different functions in your network, but they use the same infrastructure. Hence, they use the synergies between the applications. Like one needs more networking power and the other needs more compute power to better utilize the infrastructure. Those service instances can come from DriveNets. That means the networking functions, the routing functions, could be a core router, aggregation router, etc. Or they can come from a third party. Those would typically be security functions like DDoS and firewall and other type of networking functions which are not core routing. The fact that we run multiple network functions on top of the same infrastructure, or multi-service as we call it, allows us to run to get the benefits I mentioned earlier. So we get elastic scaling by using acceleration, by using a networking optimized infrastructure or hardware in order to gain better performance of applications that typically run on servers like firewall. We get great resource optimization, which drive to lower TCO, because we better use the infrastructure by using and leveraging the synergies between the different applications. And of course, we get service innovation. That means that we can deploy services faster time to market, faster time to revenue, and you have a one-stop shop. You have a one-stop shop. That means that you have a marketplace by DriveNets in which you can buy and install third-party network functions without the need to go and install those yourself. So this is how we do it. And just to conclude, two examples of the benefits you get. One is running multiple network functions on top of the same infrastructure. And so instead of having a different router and different hardware for your business services edge router, for your mobility edge router, and for your broadband edge router, all aggregating towards a core router, you can do all of these functionalities over the same hardware. So it is, for instance, easy to migrate resources from business connectivity to broadband home connectivity in cases like a global pandemic, which is far-fetched, I know. And it is also saving you the intra-connectivity between the different routers, because this is done over the fabric. You don't have to use ports in order to connect the different services towards the core router. The last example is multiple applications in a peering site. So you have peering router as well as DDoS mitigation appliance over the same infrastructure. So instead of having a scrubbing center, which is external, which you need to run external to divert the traffic towards and get additional latency and limited capacity, you can implement the DDoS scrubbing center as a cloud function, as a network cloud function inside your infrastructure, and do all the internal networking virtually over the fabric. So this is what DriveNets does. It takes the network functions you need, especially the data plane functions, and optimally implement those over cloud infrastructure. This is the right way to run network functions over cloud, and the benefits you get are lower cost, optimal scaling, and ease of innovation. That is the ability to bring new services to new markets and to create new revenue streams. Thank you very much for watching. See you next time. Bye-bye.